The tangent problem is going to really help us understand the concept of the limit, and in turn help us understand the first half of calculus, which is differential calculus, or taking derivatives, and what that means and what we're doing when we're taking derivatives. First of all, what is a tangent line? Well, tangent comes from the Latin meaning touching, and a tangent line is a line that touches a curve, specifically at one point. So you could have a tangent line here, here, there, but not here. This would be known as a secant line. Secant also comes from the Latin meaning to cut, and a secant line cuts through a curve at least 2 points. What's neat is that every single point around a circle is going to have a slope. That is, if the curve keeps on going and stops at this point, it will be heading in that direction. If the curve comes and stops at that point, it would be heading in that direction. So let's say that we have a function right here, and it starts out like this, and then it goes crazy. And suppose we want to know the slope of the curve at this point right here. Well, we would just draw the tangent line right here. And the reason why I drew the graph like this is because when we're finding the tangent line at a particular point, i.e. the derivative, we're only concerned with this region right here. Yes, it does cross through multiple points of the same curve of the function way over here, but we're only focused at this point right here. Now the paramount question is how do we find the slope of the tangent line? Every single point along this graph will have a tangent line with its own slope. But if we're focused at just this value x right here, what is the slope and in turn the equation of this tangent line? As it turns out, that is impossible with what we knew before calculus, and hence the name the tangent problem. But here's how we could do it. Here's how you could find the slope of a tangent line of a curve at a given point. In this example, let's say we have f of x equal x squared. So let's draw out this function. And as we notice from algebra, this is a parabola. And let's say that we want to find the slope of the tangent line that crosses at this one point right here called P, at the point 1, 1. So let's go ahead and draw the tangent line, which comes about right there. So let's notice that we cannot find the slope of this tangent line because we need 2 points. Recall that slope is the change of y over the change of x, which is y2 minus y1 over x2 minus x1. So we need 2 points because slope is rise over run. But if we just have 1 point, we don't know how high to rise or how far to run. So we're kind of a bit stuck so far. So we're going to start by making an approximation. Let's draw another point right here and call it Q. And now what we're going to draw is not the tangent line, but the secant line. And as we notice, that's some form of an approximation. We do have a rise, and we do have a run. Our rise being delta y, and our run being delta x. And we'll say that the point Q will have the x value right here. And let's call this x value x. Well, if we plug in numerical values and find the slope, it's not going to be exactly the tangent line. It's going to be off a little bit. Could we move Q closer to the point P? Well, let's try it. Let's move our x value in closer to 1 and put our Q here and draw the secant line. Okay, well, see, it's getting better. It's coming from here to there. In fact, we could get even closer and put our Q right here. And then as we notice, our secant line is going to get even more close. And as you see right here, the secant line is almost right on the tangent line. And you know, I could do the same with the other side. I could choose my Q to be right here and the x value to be here and get the x value closer and closer to 1. The thing to notice is that the closer we get to 1 on either side, the closer our secant line is going to get to our tangent line right here. And that is what we want, that is the goal. Now let's recall that our point P is going to be the point 1, 1. Well, our point Q is going to be the point x comma x squared. And the reason why is that when we plug in an x value, the corresponding y value is going to be x squared. So this Q has the coordinate x comma x squared. In fact, any point that you make on this line is going to be a x comma x squared. Now we have 2 points, x1, y1, and x2, y2. So therefore, the general formula for our slope is going to be x squared minus 1 over x minus 1, our rise over our run, or our delta y over delta x. As we notice, x can't be 1 anyway, otherwise the denominator would go to 0, which would make it undefined. Now I want us to know what we're doing. We are moving this point Q closer and closer to point P. We're moving our x value closer and closer to 1. However, we cannot put Q directly on P because if we did, it would be the same point. And no pun intended, but it would literally be pointless. We need 2 distinct points, even if they be infinitely close to one another. Our next step now is to make an XY table. So I'm going to make 2. The reason why we're making XM tables is because we're going to plug in an x value and find what m is, or the slope. And I'm going to use one table for x values approaching 1 from the left and the other one for x values approaching 1 from the right. So let's say that our first point is 0 and then let it get closer to 1. How about halfway in between? So let's put 0.5, and then let's get it closer to 0.9, and then 0.99, and then 0.999. So we're getting closer to 1 except for 1 itself. Now let's say on this side we start at 2 and let's approach 1 from the right. And let's get closer to 1, so let's put 1.5. And then let's get closer to still to 1.1. And since we can't reach 1, we could go in between 1.0 and 1.1 by choosing the point 1.01 and the 1.001. So when we plug in these values in for our equation, this is what we get. When we plug in 0, we'll get 1. When we plug in 0.5, we'll get 1.5. Then 1.9, 1.99, and then 1.999, and however more precise that we want to go. When we plug in 2, we get 3. Plug in 1.5, we get 2.5, then 2.1, 2.01, and then 2.001. And it seems that whether we come from the left or we come from the right, we're getting closer and closer to the value 2. So let's see what we're doing. When we choose our x value to be 2, the corresponding y value is going to be 2 squared, or 4. When you connect 2, 4 with 1, 1, it's going to create a secant line with the slope of 3. If we choose our q to have the x value of 1.5, we plug it into the equation. The corresponding y value should be 2.25. that's going to create a secant line with a slope of 2.5, and so on. So as we make our x values closer and closer to 1 on either side, we're approaching a slope of 2. And we can make the safe assumption that the slope of the tangent line will in fact be 2. The limit is the number that we are getting very, very, very close to, but we just cannot reach. And as we get closer and closer to 1 on both sides, the limit will be 2. We can neither get to 2 nor surpass 2. Therefore, the slope of the tangent line, specifically at the point 1, will be 2. So if the curve is coming this way, and at 1, 1 it suddenly stops, it will keep on going in that direction with a slope of 2. So let's write that out right here, that the slope of the tangent line equals 2. And let's take this a step further and find the equation to the tangent line. Why not? We have a slope and we have a point at 1, 1. And let's recall the point slope form that says that y minus y1 equals m times the quantity x minus x1. So let's plug in the numbers. We have y minus our y1, which is 1, equals 2x minus x1. So this is y minus 1 equals 2x minus 2. And adding 1 to both sides, we get y equals 2x minus 1. And that is the slope of the tangent line at the point 1, 1. And if we notice, that means that the y-intercept is at negative 1. And the slope is 2. So if we go up 2 and over 1, we're at that point. And therefore, that is the slope of the tangent line. So in this video, I was endeavoring to articulate the tangent problem, which is really needed to understand the concept of the limit, which is really going to be helpful in understanding what we're doing when we're taking derivatives. I hope that was helpful, and if not, then I have links in the description below and the cards above from people whom I would recommend, and hopefully that would answer some questions that you might still be having. Calculus isn't necessarily hard. It is just basically algebra and trigonometry and utilizing new concepts. And when you get to Calculus 2, you really need to brush up on your trigonometry. But as long as you understand the concepts and what we're doing, and if you have a good background in algebra and trigonometry, I guarantee you that calculus will be no trouble at all. And I want you to know to not give up on it without trying it. Not give up on your passion or what your major is and what you want to do in life. I hope you have a wonderful day, and if you're watching this because you're taking the class, I hope that you have a wonderful semester, and thank you.